My dear students, in the last class we have discussed about the electric potential due to a point charge at a distance r. Hence we got conclusion that V is equal to 1 by 4 pi epsilon 0 Q by r in air medium for a charge Q at a distance of observation point r. That is electric potential due to a charge Q at a distance of observation point R is found to be V is equal to 1 by 4 pi epsilon 0 Q naught by Q by R in air medium. That is, electric field is qualitatively explained as the quantity that determines the direction of flow of charge. Clear? Here, electric potential is a scalar quantity, but it gives the direction of charge flow. Then, quantitatively it is defined as the amount of work done in bringing a unit positive charge from infinity to that point without acceleration against electrostatic force is called electric potential. It means when a unit positive charge is brought from infinity, it is called electric potential. Instead of 1 coulomb or 1 unit positive charge, if I brought a charge, then the work done is called potential energy. Listen to it. It is the work done in bringing a charge from infinity to that point without acceleration against electrostatic force. It means potential energy is equal to amount of charge brought from infinity to the electric potential. I can write it here. W is equal to Q0 into V, or 1 by 4 pi epsilon 0 Q0 by R. Clear? Let us imagine this is a point charge Q1 and this is another point charge Q2. Are placed at a distance of apart R. Then for two particle system or for 2 point charge, potential energy, or we can say work done, is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R. Clear? But electric potential is a scalar quantity. It can be added algebraically. Clear? It can be added algebraically because it is a scalar quantity. Hence, the net potential due to system of charge is a scalar addition. It means ordinary addition. Clear? That is called principle of superposition of electric potential. Similarly, I can say electric potential energy is also scalar quantity. Electric potential energy is also scalar quantity. So, for a 3 particle system, the total potential energy is added up. Let's see. For 2 point charge. Let us imagine for 3-point charge. That it will be Q1, Q2, Q3. Let this is R12 and R23 and R13. Clear? Then net potential energy is equal to W12, W13 and W23. Clear? I can write it in for air system 1 by 4 pi epsilon 0 Q1 Q2 by R12. Here Q1 Q3 by R13, Q2 Q3 by R23. Clear? This is for 3 particle system. For system of charge, if the system consists of n particle system, again n particle system. The system consists of n number of particles. Net potential energy is equal to W12, W13, W14 dot. Clear? Similarly, W23, 24 dot. W12, then W34 dot. N minus 1. Clear? I can write it as a 1 by 4 pi epsilon 0 Q1 Q2 by R12 dot. How much? Qn minus 1 Qn by n minus 1. Clear? I can write it as a 1 by 4 pi epsilon 0 Qi Qj by Rij, where I is equal to 1 to n, I not equal to j, and I must be smaller than j. Listen to me. When I is equal to 1, j is 2, 1, 2, 1, 3 up to n. Then I becomes 2, 2, 3. Okay. In such a way, we can find out the net potential energy. Clear? Listen to me. I would like to say that potential energy is a scalar quantity. So it is added algebraically. Okay. So here net potential energy for n number of particles total. Listen to me. Let n is equal to, I would like to say that n is equal to 2. Means I is 1, n is 2, 1, 2. Complete. By R. Clear? Next. For 3 particle system, n is 3. If n is equal to 3, then Q1, Q2, then Q1, Q3, then I becomes 2, 2, 3. This is 3, Q1, Q2 by R12, Q1, Q3 by R13, Q2, Q3 by. Similarly, we can find out for a, if it is a square, 4 charges are placed at 4 vertices of a square, then n is equal to 4 In such a way, we can find out the net potential energy of a system of particles. Clear? Next. Now the relation between electric field and the potential. Let dW be the work done. Due to displacement of a charge Q0. Through a distance dr towards a source charge q respectively. Listen to me. Let this will be a source charge. Let a charge is brought from infinity to that point. Let the displacement will be dr and the work done will be the dr. W. Therefore, F is equal to 1 by 4 pi epsilon 0 Q0 by r square, that is electrostatic force. I can write it as a dW is equal to F dot dr F dr cos theta, theta is equal to how much? Theta is pi and cos theta is equal to -1. It means I would like to say that two similar charges or like charges repel each other. But to make them closer, we have to do some work. It means we are doing some work against it. And that energy gets stored. That is called potential energy. Clear? So, against electrostatic force, some work is done. So, that's why theta is pi and cos theta. Hence, dW is equal to F dr minus F dr. So, instead of F, I can write Q0E clear? dW by Q0 is equal to minus ADR. And we know that work done per unit charge is nothing but the potential difference. Clear? So, I can write it as a dV is equal to minus ADR, or I can write it as a negative line integral of electric field is negative line integral of electric field is electric potential. Clear? So, whenever the electric field is integrated, it forms what? Electric potential. Clear? This is also written in the form of dV is equal to minus EDR. Then I can write it as E is equal to dB by dr. It means negative scalar gradient. Negative scalar gradient. Gradient means variation with respect to distance. So here potential varies with respect to distance. So it is called potential gradient. So variation of potential with respect to distance is called potential gradient, and the negative of that is called electric field. But we know earlier in work for energy that if scalar gradient of potential gives a vector quantity, then it is a conservative force. Listen to me. Potential is a scalar quantity, but potential gradient is an electric field, and electric field is a vector quantity. So electric field is a conservative field, and electrostatic force is a conservative force. Clear? Did you get it? So, does electric field is a conservative field? Yes, electric field, because when we take the negative scalar gradient of electric potential, it gives a electric field, and electric field is a vector quantity. Clear? Next, we can check. Whenever we are going to the line integral of electric field, it gives a potential. It means it depends upon the initial position and final position. It does not depend upon the path followed. Or we can say, if the work done by this force is independent of path, then it is a conservative field. Clear? So here we conclude that electric potential is a negative line integral of electric field, or the potential, negative potential gradient gives rise to a electric field. Hence from this we conclude that electric field is a conservative field and electrostatic force is a conservative force. So some people say do it in alternative method also, we can prove it. In place, electric field intensity E is equal to how much? F by Q0, that is 1 by 4 pi epsilon 0 Q by R square. Similarly, electric potential V is equal to W by Q0, it is found to be 1 by 4 pi epsilon 0 Q by 1 by 4 pi epsilon 0 Q by R. If it is differentiate with respect to distance of observation point, then dV by dr, that is derivative of 1 by 4 pi epsilon 0 Q by R. Here 1 by 4 pi epsilon 0 Q is common. D by dr 1 by R, it is found to be 1 by 4 pi epsilon 0 Q. 1 by R derivative is 1 by R square. It is found to be minus 1 by 4 pi epsilon 0 Q by R square. It is nothing but the electric field. Look at it here. 1 by 4 pi epsilon 0. Hence E is equal to minus dB by dr. This is also alternative method. Clear? Did you get me? Next. According to Gauss's law of electrostatic, electric field intensity inside hollow conductor is 0. If so, what's about electric potential? Listen to me. Let it be a hollow conductor. Ready, sir? Clear? No charge reside inside hollow conductor. Therefore, electric field, charge is 0. Therefore, from Gauss law of electrostatic, phi E is equal to q by epsilon 0, and it is E dot ds. As the charge is 0, electric field inside 0. Clear? But according to relation, E is equal to minus dV by dr is equal to 0, because the electric field inside 0. Hence dV by dr is 0. Whenever the derivative of a physical quantity is 0, it means that quantity is constant. That's why V is equal to, V means electric potential is constant. Graphically we can represent it as a clear. So it is the variation of graph between electric potential difference with the distance for a hollow conductor. Clear. So inside hollow conductor, what happens? Electric potential inside and surface are equal. Clear. And it gradually decreases as we move away from the center of the hollow conductor. Clear? Now the question arises. In a heavy lightning storm, a man is inside the car. What he will do? Option number 1. He will come out of the car and lie on the road. Option number 2. He will come out of the car and run under the tree. Option number 3. He will come out of the car and lie on the road. And option number 4 is he will remain inside. What are the 4 options? Run under the tree. Option number 2, lie on the road. Option number 3, touch the electric pole. Nearby. Option number, remain inside the car. In a heavy lightning storm, a man is inside the car. What he will do? Come out of the car, run under the tree. Come out of the car, lie on the road. Come out of the car, touch the electric pole nearby. Option number 4, remain inside the car. What he will do? Answer 4 is correct. Clear? Because electric potential inside and surface are equal. Hence there is no potential difference. It means no work done. Clear? Hence the person saved himself. If electric field at a point is a function of position, electric potential at a point is a function of position, as Vx is equal to 4x square plus 2x. Where x is distance of observation point measured in meter. Find the electric field intensity at x is equal to 2 meter. Look at it. Potential is given. Vx is equal to 4x square plus 2x. And asking for electric field at x is equal to 2. Clear? Therefore, E is equal to dV by dx, that is negative. Scalar gradient, here x is the distance of observation point. So, scalar gradient means dV by dx. If you found it, minus d by dx, how much? 4x square plus 2x is equal to 4x square, 8x plus 2. At x is equal to, E is equal to minus 18 volt per meter. X is 2, 8 to the 16, 16 plus 2, 18, minus sign is there, to minus 18 volt per meter. Clear? Okay? Now we discuss about the potential energy, then we have discussed about the relation between the electric field and potential and some questions related to it. Now we are going to discuss about the electric dipole. Electric dipole. In electric field class number 3, electric field class number 3, we have discussed that what is an electric dipole. Electric dipole is electric dipole consists of two equivalent opposite charges when separated by a small distance, or when two equivalent opposite charges are separated by a small distance, it forms an electric dipole. Let AB is an electric dipole. Okay, let it is A and B having charge minus q and plus q. The distance between the two charges is called dipole length. Let it will be 2L. Clear? Then we have also discussed about the ideal electric dipole. And we conclude that for an ideal electric dipole, the magnitude of the charge tends to infinity, while the distance of separation tends to 0. Clear? So, ideal dipole is also called as point dipole or a short dipole. Then, electric dipole moment. It is P vector. Electric dipole moment can be defined as the product of magnitude of either one charge and dipole length. It means P vector is equal to Q into 12 vector. That is magnitude of either one charge and dipole length. Clear? So P vector is equal to Q into 12 vector, or I can write it as a 2QL vector. So dipole moment is a vector quantity and it is always directed from negative to positive. Clear? Now, its unit and dimensions will be well discussed in the class 3 electric field. Now, the line that passes through the two charges of the dipole is called axial length. So, this line is called axial length, while this line is called equitorial line. It means the line that passes through the center of the dipole and perpendicular to its dipole length is called equatorial line. Now we are going to discuss the electric potential at any point, and from there we can easily find out the electric potential at axial line as well as equatorial line. Okay, let's see for that. electric potential at a point, at any point, of any line of an electric dipole. Look at me. Let AB is an electric dipole. Clear? Let us draw any line that passes through the center of the electric dipole. Hence, O is the center of the electric dipole. If 2L is the total distance, clear? Then this distance is L and this distance is L. And this line is inclined at an angle theta with the dipole length. Clear? Let us find any position small p at a distance r from the center of the dipole, where I want to find out the net potential. Clear? So listen here, potential is a scalar quantity. The first point we have to remind is potential is a scalar quantity, it has no direction. Second thing is electric potential is a positive for positive charge and a negative for negative charge. Clear? So look at in the triangle ONA. In the triangle ONA, this length is L. Clear? This angle is theta. So I want to find out ON, and it is to be L cos theta. Clear? In triangle OAN, cos theta is equal to base by hypotenuse, ON by OA. Hence ON is equal to OA cos theta, implies ON is equal to L cos theta. Clear? Similarly, in triangle OMB, OBM, OB is also L cos theta. So the dipole length is AB. How much? 2L. Clear? Then electric dipole moment capital P is equal to charge into length. That is 2QL. Clear? So I would like to find out let P be the observation point on any line inclined at an angle theta with dipole length. Clear? With dipole length at a distance r. Clear? Therefore, electric potential at P due to charge at A is how much? B is equal to 1 by 4 pi epsilon 0 q by AP. Listen to me, as R is very large compared to L, we can assume that this theta angle is very small, so I can assume that AP is approximately equal to Pn, and I can write it as a 1 by 4 pi epsilon 0. Pn means total distance is R. This distance is L minus cos theta. So Pn is how much? Pn is OP minus ON, that is R minus L cos theta, 1 by 4 pi epsilon 0 q by R minus L cos theta. Similarly, potential for positive charge is placed at A while negative charge is placed at B, and we know that potential is positive for positive charge and negative for negative charge. Hence, BB is equal to 1 by 4 pi epsilon 0 q by PB. So, PB is equivalent to PM as we neglect the theta. So, at that condition, this is R and this is L cos theta. So, 1 by minus q here, because minus q is there. 1 by 4 pi epsilon 0 minus q by R plus L cos theta. Listen to me. So potential is a scalar quantity. Therefore, net electric potential at P is VA plus VB. Clear? Because potential is a scalar quantity, it can be added algebraically. If so, then V is equal to 1 by 4 pi epsilon 0 q by R minus L cos theta plus minus of this. So plus into minus, minus 1 by 4 pi epsilon 0 minus q by R plus L cos theta. So plus minus minus. So I can write 1 by 4 pi epsilon 0 q 1 by R minus L cos theta minus 1 by R plus L cos theta. Clear? So 1 by 4 pi epsilon 0 q R plus L cos theta minus R minus L cos theta. Whole by R square minus L square cos square theta, that is A square. A minus B plus B is A square minus B square. So L cos theta added up, while R get cancelled. So this is Q and L cos theta, 2L cos theta. Instead of Q into 2L, we can write it as a dipole moment. Okay? So V is found to be 1 by 4 pi epsilon 0 2QL into cos theta by R square minus L square cos square theta, or 1 by 4 pi epsilon 0 2QL is P cos theta by R square minus L square cos square theta. This is the expression for the electric potential at any point P. Clear? So if we neglect this dipole length, if the dipole length is get neglected, then for short dipole L tends to 0. If L tends to 0, then this L square cos square theta factor 1. Then V is equal to 1 by 4 pi epsilon 0 P cos theta by R square. Clear? Now the question arises, sir, if this is the expression, then how can you find the axial and equitorial? Listen to me. For an axial line, the line that passes through the dipole and parallel to its dipole length, it means theta is equal to 0 degree. that is axial line B. So that line is parallel, theta is equal to 0 degree. Theta 0 degree means cos theta is how much? P cos theta. Cos theta is 1. So V axial 1 by 4 pi epsilon 0 P by R square. Clear? Case 1. Case 2. This is for axial line. For equatorial line, theta is pi by 2. For a dipole, let this is a having charge plus q and minus q, bq. So for a dipole, the line that passes through the center of the electric dipole and perpendicular to it is called how much? Equatorial. Equatorial line at a distance r. Let this is small p. Okay, r. Then cos theta is 0. Therefore, B equatorial is 0. Very, very important. Clear? Now the question arises, sir, give an example where electric field exists but not electric potential. Electric field exists but not electric potential. That is, at any point on the equatorial line, electric field exists. That is 1 by 4 pi epsilon 0 P by RQ. 1 by 4 pi epsilon 0 P by RQ. But equatorial line potential is 0. Give an example where field doesn't exist but electric potential exists. That is, inside the hollow conductor, electric field is 0 but potential exists. Okay. Thanks to one down. Thanks for watching. Next class we will discuss about the equipotential surface and some regular questions that comes or appear in the regular exams. Okay. Till then, bye. Have a good day.